Welcome to tutorial number 5 of the pm4py tutorial series. In this tutorial, we will be looking at more event filters or event log filters. In particular, we will be looking at filters that are pre-built into pm4py that are extremely useful when you're crunching and merging your event data. So my name is Sebastian van Zelst, and I'm a researcher at Fraunhofer Institute for Applied Information Technology, and I'm also affiliated with the Process and Data Science chair of RWTH Aachen University. Of course, if you're interested in reading my research, you can definitely take a look at my scholars, Google Scholar page or my homepage, which is sebastianvanzelst.com. But today I'll be focusing, of course, on pm4py as always. So what we're going to do is we're going to look at some basic event data filters. And first of all, very short recap is event data, as I hope you know when you've been watching this tutorial series, consists of sort of a bunch of rows, which we can represent as a CSV file or preferably an XES file, as I've been showing in previous tutorials, where we're able to basically see what activity was performed at what point in time. So for example, here in this example table, we see for some order with ID 1233, we see that the create order activity has been performed at 29th of November 2019 at 5:14 in European time formatting. In the remainder, when I'm talking about a trace, I'm talking about the sequence of activities that we have been observing for a specific order or a specific case. So for example, if I have some order with ID 1337 and I've seen that there were some activities performed and I'm just using simple labels here, A, B, C, D. So that's a trace recording the behavior ABCD, so the sequential ordering of the activities ABCD, where ABCD can be any type of activity. I'm abstracting a bit here from the exact activities. And for another order 1338, I might see the scheduling ACBD. So I might observe that instead of executing B after A and then C after B, I have executed C after A and then activity B after C, and I finalize with activity D. Again, these letters just represent any arbitrary activity. I don't care really if it's a registration, it's just for registration purposes. Then there might be another order 1339 where I see A, C, B, D, E. And then finally, there might be another order, maybe 1334, which also records the trace ABCD, or the trace for order 1334 also records the sequence of activities that have been performed ABCD. So when I talk about a trace, I refer to, let's say, a single execution, an instance of a process that is recorded in the event data that describes the sequential behavior of activities. And multiple traces can actually represent the same sequence of activities. Like in this example, there's two cases, 1337 and 1334, and they both describe ABCD. But in some cases, I'm referring to a trace variant. So for example, it can be that in our data, actually, the orders 1332, 1337, and 1334 all have a trace that describes sequential behavior ABCD. And when I'm talking about a trace variant, I'm talking about, the behavior ABCD. So ABCD is a trace variant that we observe in the traces recorded for orders 1332, 1337, and 1334. And for example, ACBD is another trace variant that I observe in the traces recorded for orders 133, 1338, and ACBDE can be a trace variant that we observe for orders 1335, 1336, and 1339. So the concept of a trace variant, and I'm explaining this because later I'll be using some filters that allow you to directly filter on variants. They basically allow you to extract, or they describe, this abstraction describes the same sequential scheduling of the activities. So the same sequential behavior of activities. So in that sense, there can be multiple orders that have all kinds of different, parameters, a different customer or a different purchase order or a different item. But in the end, the sequence of activities that was performed for those same client or same purchase order is in fact the same. So then we say they describe the same, they have the same process variant, trace variant, etc. So that's something that if I talk about a trace, I talk about an individual execution. And if I talk about a trace variant, I'm talking about sort of a group of similar executions. So multiple traces can describe the same trace variant. Okay, now I'm going to show you a bunch of fairly simple filtering functions in pm4py, which are quite easy to invoke. And they allow you to filter in all kinds of different ways. And I'm going to use the same event data that I've been using before. So I'm going to use the running example event data, which describes in total 6 instances of the process that is modeled by this simple PPMN model in this slide here. So basically, the data will, and it's free of noise in this case. Of course, filtering is usually used to filter out noise, but in general, example purposes, I'm using this simple example. And to just briefly recap what this process is about. So first, there's a registration, a register request activity that will always be performed. After which we have the concurrent scheduling of the check ticket activity concurrently with a choice between the examine thoroughly or the examine casually activities. And then finally, a decision is made if something were to be wrong in either the examination or the ticket check, then we have to reinitiate our request. And if everything went well, we either pay a compensation or we reject the request for compensation payment. So that's the scope, that's the data. And if you've been seeing the previous videos, this should be fairly familiar to you. Great. So first group of activities allows us to filter on start or end activities. So why is this interesting? As it turns out, when you go into the real world and you extract an event data set, it can typically be that you extract the event data from, I don't know, January 2017 until December 2020, for example. But obviously, process instances typically don't start at the beginning of the year. There might be several instances that have been running from before you started your extraction phase, and there might be several instances still running into 2021, although you've only extracted until December 2020. Right, so it can be that, for example, in our data, even though for order 1338, for whatever reason, activity A was scheduled and was executed as well, it was executed, but it's not recorded in our data because it, for example, happened prior to when we started recording our data. And similarly for order 1334 here, it could be that actually we still need to execute, for whatever reason, activity D. So that might also not be part of our event data. So whereas the true execution of the process instance for the order with ID 1338, in fact, activity A did happen, it's not in our data. And the same holds for order ID 1334, activity D, whatever it might be, it did happen, it's just not recorded in our data. So filtering on start and end activities allows you to filter out certain cases that for whatever reason, or certain traces in your data that for whatever reason have a very infrequent start or end activity. And I'm now going to show you how to do that in pm4py. So here I am now in my PyCharm editor, and I've loaded this event data in this line 6. And now I happen to know that my register request activity is the only start activity in this event log. So, and the way how I can filter my event data on a set of start activities that I'm interested in is basically extremely simple. I just type pm4py dot filter underscore start underscore activities, and the first parameter that I provide is my log, and my second parameter is a collection of start activities that I'm interested in. Obviously, such a collection is pretty easy to compute. I mean, you just need to iterate over the log. Like, basically, I can show you. You can basically say, okay, I'm taking each trace in the log. There's various ways to do this. This is a very simple way. And then you can, for example, let's say we have some dictionary D. And yeah, so basically what you do is you add the concept name of the first event for that trace. So right, so the trace is a list of events. 0 is the first event, and as you probably know, you can usually fetch the name by typing concept name. And that's basically it. So here I can make a dictionary that contains all the all the activities that at some point start at the beginning of the trace. And the value is just the number of times it occurs. And then I can just basically, based on the dictionary, I can, cross out all the activities that don't really, that have a fairly low frequency, and I obtain a set of keys of my dictionary that are the activities of interest, right? So that's fairly easy. So assume that I've done that. And for this, if I would run that code for this example, I would just observe that register request is the only activity that happens as the first. Anyway, so if I filter the event log using using just the set containing the register request activity, then here in the bottom of my screen, I can inspect my end result, and I see that. Let's first take a look at our event log. So that's the variable I'm just highlighting. So this is the sample event log, and if I look in its product attributes, I see a list of traces, and here I see all my traces: 0, 1, 2, 3, 4, 5. That's the 6 traces I've been talking about. And basically, these are all lists of events. So trace 0 has 9 events, trace 1 has 5, trace 2 has 5, trace 3 has 5, trace 4 has 13 events. Actually, trace 0 has 1 repeated execution of the loop, and trace 4 has 2 repeated executions of the loop. And trace 5 again has five events. So obviously, all of these traces, if you've also seen the process, the model that sort of represents the execution of this process, the first event is always register request, right? So if I go into trace 0 and I'm going to take a look at the events here, I see indeed the first event has a register request, is a register request activity. So if I filter the event log that I just did on all traces that have register request as the first activity, then I should actually just obtain the original event log. And if we take a look now here in this variable filtered, which is the result here of the code that I've just triggered, then actually we see again that filtered variable has 6 events, 6 traces, like the original event log. And if I then again take a look at its protected attributes and I take a look at the traces that are there, I again see trace 0 has 9 events, trace 1 has 5, trace 2 has 5, trace 3 has 5 events, trace 4 has 13 events, and trace 5 has 5 events. So I see indeed that the filter retains all traces, which is exactly as we expect. Now, if I add a typo, like I did in this next example here, and I can even write another start activity if we like. So wrong start activity. So I'm now going to filter basically I'm going to filter the the event log on any trace that has either register request typo exclamation mark and wrong start activity as the first activity, I will have zero. I will have zero traces left because none of my traces has any of these strings as the first activity, right? So if I progress in my script, you see indeed that the filter event log is now empty. So all the traces have been removed. That is something that automatically is done. So this filter actually removes all empty traces directly. So I now have an empty event log in my filter attribute. Now, obviously, as I said, we can do the same for end events. So again, you can easily make a very short, simple script that creates a distribution of the occurrences of the different activities as the final event of any trace. Again, you can just iterate over the log, but you just take the last element of each trace and check the concept name value there, and you again create a distribution. It's one of many ways to do that. And in that sense, you can also filter on end activities, and actually you can also just give one argument for this filter. So here I have this filter end activities filter, which if I try to filter the log on pay compensation, I have now here below in my filter event result, I have 3 cases remaining, right? So recall that we filtered on, let's take a look, pay compensation, right? Remember there was 2 options to finish in this process, pay compensation or reject request. So in this case, I filtered only those traces that end with pay compensation activity. And we see that 3 out of the 6 traces, actually here we see that in the filtered length of my event log is 3. So we retain 3 traces that actually end with an end activity that is the pay compensation. And if we take a look to our traces here, so trace 0 has 9 events, and if I look at its individual events, I have to go a bit down in this hierarchy. Then we see that, the pay compensation, not just the reject request, the pay compensation activity is there, and the same holds for trace, the second trace in this log, which has 5 activities here. So again, if I go into its protected attributes and I check its underlying list, I see that the final event is again a pay compensation. And of course, for the last trace, which again has length 5, if I look in its underlying list, I see that it again has a pay compensation. So this allows you to also filter on the end event. So these 2 filters are extremely useful in the sense that they allow you to very easily filter on start and end events. And obviously, you can also create such events using the Lambda function that I presented in the previous tutorial, but this is just a fairly direct way to do that. Okay, so that is filtering on start and end event. Now, a second type of filters that we implemented that are very useful to use having the same invocation style are attribute filters. So as I've also presented before, event data and specifically events, but also traces, they can have various attributes. So we've shipped pm4py with some filter functionality that easily allows you to specify for a specific attribute, okay, I want to filter this event or trace attribute, and I want to have I want to allow for this collection of values. And of course, again, I have a few simple examples on how to filter on attribute values. So I'm back in my PyCharm instance. So for example, as you know, we've been also tracking in the data resource information. So if I would take a look in the original event log, And I go again, I'm going to check the traces, which is here in this list object, the protected object of the log. And I open, for example, the first trace, and I'm going to look in the individual events. Then I observe here that event 0 has, for org resource, has a value of Pete. And the second event there with index 1 in that underlying list has org resource Mike. And then the third event has a resource called Ellen that is working. So what I can do is I can basically um, write a script where I'm going to filter my event log, and I'm going to basically going to filter out all the a given set of values for a given attribute. So that's what you see in currently on top here in the highlighted in the highlighted line here. You see that I'm executing a filter. I'm filtering event attribute values. I take the log as my input, and I say I want this attribute or resource, and I want to have it have value Pete or Mike. Now, what's important about this specific feature, and you can see that also in the line below the blue highlighted line, is that this has an additional parameter called level. And that's the level at which you would like to apply this filter. By default, this level is set to cases. So I could type level equals cases. So the default operation is that it retains any trace that has any event specifying that either Pete or Mike is executing at least one event basically of the trace. So it retains the whole trace that at least says, okay, I have an event that is executed by either Pete or Mike, right? So if I, as opposed to the other level at which you can operate this filter, which operates the level of events. And that type of filtering will actually remove all events that do not adhere to having Pete or Mike as a resource. So if I continue in my in my debug here, so if I now execute the blue highlighted line number 14 in the top of my screen here, and now get the result of that call here that I just did, you will actually see that my filtered log contains 6 traces again. You see that here. And if I go deeper into my event log, and if I check all the traces, you see again that none of these traces is touched. So that means that every trace has at least Mike or Pete doing something. And as a consequence, I basically have the original event log back. So in every trace, Pete or Mike does something. Now, if I, as I said, if I invoke this same method, but I invoke it at the level of events, I'm going to drop all the events that basically that do not have Pete or Mike executing them, right? So if I now invoke this blue highlighted line 16 here, again, my filtered event log should contain 6 traces, because we've seen that every trace contained at least one event where Mike or Pete was active. However, what will change now in my result is that if I go into in depth and I'm checking my traces, you'll see that the length of these traces is much shorter. And indeed, trace 0 now has only 3 events, and those are all the events where either Pete or Mike is doing something for the trace. So if I dive down here, I see that the first event that we retained is the register request executed by Pete. Second event that we retain is the examine casually by Mike, and then Pete does the check ticket again. So this is actually quite useful, because you can basically apply this on any categorical attribute that you have. Also numerical attributes, you can you can basically give a range as an input, and pm4py automatically detects that range for you. So but in the end, any data, we always have a finite set of attributes, of course, in an event log, as long as the event log is a finite set. So that's about filtering on the event log attributes. Then I can also do this at the trace level. So even though I had event attributes that are filters that are active either on a case level or a case annex or trace level or an event level, I can also filter out traces with certain attributes. And there the idea is that you basically check just the attributes of the trace, and you again verify whether or not the values recorded are there. So for example, in the blue highlighted line on top here, line 18 of here above, I'm filtering the event log, and I'm saying, give me all those traces that have for concept name, so the concept name attribute, either a 3 or a 4 in this simple example. So this means that I'm going to only have 2 traces in my filtered event log that have either a value 3 or a value 4 as an identifier, right? So if I execute it, I look here below in my debug screen, and I see here that the filtered event log indeed has 2 traces, which is exactly what we expect. And if I dive into my underlying list of traces, I again see that's a list of length 2, and I see that I've retained a trace with length 9, and indeed with concept name 3, and another trace at length 5 with concept name 4. So indeed, I retained the traces with attribute value 3 and 4. Another attribute, as you can see here on the trace level, that I could actually filter on was the creator attribute, which is having a value Fluxicon Nitro, but all events in the data that I'm using have this additional attribute. It's the tool that has generated this event data back in the days. All right, so if I go back in the next blue highlighted line, the next filter, again, still on attributes, I have almost exactly the same as the filter I executed before. So again, I have a trace attribute value filter. I use the concept color name key to filter. I'm using values 3 and 4, but I've added this parameter retain is false. In fact, a lot of the filters that I'm showing, also some of the previous filters, have this retain option. And basically the only thing that the retain option does, so normally by default the retain option is set to true. If you set it to false, it inverts the filter, so it basically negates the proposed filter. So if you would say I want to not retain all, so retain is false, all cases in this log that have a concept name trace attribute with either value 3 or 4, that means I will get all other traces that have a value different from that. So it's an easy way to negate certain filtering criterion. So if I execute this specific call, I just executed that specific call. Sorry. Then what do we get? Indeed, we get an event log with 4. As you can see here, event log of length 4. So there's 4 traces in the event log. And if I inspect it and I dive deeper into the underlying traces that are there, I will see that the traces that I've retained are a trace with a concept name value 2, a concept name value 1, 6, and 5. So indeed, concept name values 3 and 4 are not in my resulting event log. So those were a few very simple examples that show you how you can filter on attributes, both on the event level and on the trace level. And obviously, you can basically go crazy on these filters. Then I've been already talking before about variance, and now I'm coming back to that concept, so the concept of trace variance, because we can also filter on trace variance. And the idea is that you can specify a list of variance that you would like to retain. Um, right. So, for example, if I'm interested in retaining all variants in this example that at least occur 3 out of 8 times, then we all agree probably that the middle trace, I will show that again. So the middle trace variant only occurs twice, namely for order ID 1333 and 1338. So that does not occur at least 3/8 times, right? Because in total we have orders 1332, 1337, 1334, 1333, 1338, 1335, 1336, 1339. So in this example here, I have 3 variants spread over 8 different cases, or recorded by for 8 different cases. So I would remove the second, all traces that adhere to the second variant. And this is something you can also do in pm4py. And what you can basically do is same manner as I've shown you before, uh, for for the for filtering start and end events. You can basically count how many variants there are for each type. So pm4py has this get variants function that I've highlighted in line 22 here. And if I execute it, I have a variable called vars, which are the variants. And that object, that vars object that I return here, is a dictionary. And the key of each dictionary is, for both performance and hashability reasons, is a string that basically lists each activity separated by a comma. So it's basically a comma separated list where each activity in that variant is listed, and then a comma occurs. And then the value is actually all the traces that describe this specific variant, right? So if I, for example, take a look in my variants, then because it's a dictionary, I can iterate over its items and I can get the keys and the values. So I'm now printing the first key. And if you look down here in my my console, you see that this variant is register request, examine casually, check ticket, decide, reinitiate request, examine thoroughly, check ticket, decide, pay compensation. That's the variant described. And there is in this case, this would be the list. I'm printing now the list of traces that adhere to that variant. And in this data, as I've shown you, each trace is there's only unique variants in a way. There's every trace describes a unique variant. There's no 2 traces that describe the same variant. So in total, I should print here 6 lines, so each being a unique variant. So register request, check ticket, examine casually, decide, pay compensation is another variant. And there's actually the trace with concept name 2 is describing that. Register request, examine thoroughly, check ticket, decide, reject request is another variant described by trace 1. Then we have register request, examine casually, check ticket, decide, pay compensation described by trace with the concept name value 6. So we have seen 1, 2, 3, and 6. So still traces 4 and 5 are remaining. So we have a very long trace. I'm not going to spell that out loud, but that's described by our fifth. Actually, it's our fifth trace, or trace with value number, concept name, value number 5. And finally, we have register request, check ticket, examine thoroughly, decide, reject request, described by the trace with concept name 4, as you can see in the last print. But I hope you observe that if you trigger this pm4py.get variance, you basically get a subdivision of your log. So all the traces of your log are there, and they are categorized per variant. So to score each variant, you can basically easily take the length of the list that it described and divide by the total number of traces in the log. And then you have the occurrence percentage of the variant that you're interested in. And again, you can easily say, okay, I only want to retain those variants that occur at least so many times. And I think in future releases of pm4py, we will also definitely add a functionality that filters this. But in the current release, we basically expect you to do this pre-processing yourself. As I said, we might introduce that later. Obviously, it's not such difficult pre-processing to do yourself either. So, for example, here in line 27, I'm now going back here below in my debugging console. I'm going to close my filtered I'm going to filter again my event log, and I'm just going to filter it on a on one specific variant. It's important to note that you can give a lists of activities as an input. So pm4py under the hood will translate this also will translate this to the right underlying format. Right, so where the variants are actually a string, this is for hashable reasons. You can just provide a list of activities, basically, so internally we will do again translation to the right underlying format. So now if we filter the log on the register request, check ticket, examine, casually decide, pay compensation, we will get exactly one. We will get exactly one trace in our filtered log. Here we see, indeed, I've just executed this line here, line 27, 28, filtering on the variant just described. And we see it has length 1. And if I drill down, I see there's one trace with 5 events, and it should describe register request, check ticket, examine, casually decide. And if I take a look at the list of events, which here we indeed see that we start with the register request, a check ticket, examine, casually decide, and pay compensation. So I think in my next example, I'm filtering on a non-existent variant. Yes, so the variant that I just described, register request, check ticket, examine, casually decide, reject request. It's the line I just executed on line 30, 31. There is no variant that is describing this register request, check ticket, examine, casually decide, reject request. And hence I have an empty event log, as you can see here. One important thing to note is that you can also directly already give as an input a string with comma separated activity names. That should also directly work for this variant filter. So both should work fine. Okay, then let's consider the next type of filters that we implemented in pm4py, which we call directly follows relation. So directly follows relation is fairly simple. A directly follows relation implies that if I observe some activity and it's directly followed by some other activity, it adheres to a directly follows relation of that type. So for example, if I'm interested in all the variants or traces that describe a variant that describes the relation AB, then in this example, 3 traces will remain because, and that's the first batch of traces, so 1332, 1337, and 1334, because this is the only variant that describes first an activity A and it's directly followed by activity B. Right, so the second and third variants, they don't have an activity A that's directly followed by an activity B, because in both examples, there is an activity C in between. So if I would apply the directly follows relation filter with input A, comma B, then the only traces I would retain are the traces describing the variant A, B, C, D. So that would be in this dummy example, some orders with IDs 1332, 1337, and 1334. Alternatively, you can also filter on what we call an eventually follows relationship. And that is basically allowing you to have an arbitrary number of events in between the arguments. So for example, if I would like to filter on an eventually follows relation a comma e, then I would drop the first two invariants, because the first two invariants, they do not describe an activity A followed eventually by an activity E, because activity E in those two cases does not occur. So if I would apply activity eventually follows relation filter with activities A and E, I would basically drop the first two. Note that if I would apply this relation on filter relation a comma e, a comma d, sorry, so I would not filter on a comma e but on a comma d, then all the traces would remain, because in every trace a is at some point followed by d. But again, if I apply if I check for the relation a comma e, then the first and a second trace would disappear. So I can do that in pm4py as well. And obviously, the names of these filters are fairly straightforward. So you have a filter pm4py that filter underscore directly underscore follows underscore relation, which takes as an argument basically an event log, and then a list of pairs where the pair basically represents the relation. So if I execute, and it basically the filter will retain any trace that has, for example, in this case, the check ticket activity directly followed by examine casually. So let's execute that. And now let's go down in my debug overview, and I'm going to take a look in my filter event log. So I've retained two cases. So remember that I checked my directly follows relation. I checked for check ticket examine casually. So these two traces that remain in my filtered event log, I'm going to drill down into the traces here. So I have a trace concept name value 2 and 5, and I'm going to inspect them. So I'm going to check the underlying list of events. And there I should see somehow that the check ticket is directly followed by examine casually. So let's take a look. I'm here in the list of events of the first trace in this filtered log. And I see that this event is check ticket and examine casually is the next. So that's correct. Now let's take a look at the second trace that has 13 events. Again, I just have to have one witness of this directly follows relation. I'm sorry. Let's take a look in the underlying list of events. It's quite a lot. So again, I have to find check ticket, examine casually. I see here I see examine casually followed by check ticket. So this is not okay, but I'm continuing. And here event 05 and event 06, indeed, I see a check ticket followed by examine casually. Also, this function, like most other filtering functions, has a retain option that allows you to specify whether or not you want to retain cases that are having this, or the opposite, whether you want to remove them. And eventually follows, we can also do that. So we can say, give me all traces that have examination that is casual, and then finally get rejected. So if I run that, so again, I've just executed this line here. Filtered is pm4py filter eventually follows relation examine casually reject request. If I do that, I get all traces that after examine casually event or event describing activity happened, I at some point see a reject request. And when I take a look, I see that this event log has just one trace. So there's one trace that fulfills this property. And if I go into more detail, let's take a look. It has 13 events. Obviously, the longer the trace, specifically with loops, the higher the probability of hitting match. I should somewhere see an examine casually. Well, I see it already here. So the second event describes activity examine casually, and indeed it was rejected finally. So somehow this was an example where at least once an examine casually was executed and finally rejected. Again, note that there can be an arbitrary number of stuff in between. So it just has to be matched once. It's not the closest match. It's any match that we can make in the trace. Okay, so then we're almost at the end of these filtering built-in filters, because there's one more one more type of filters, which is also, of course, very natural and I think super useful, and those are basically time range filters. And the idea is actually quite simple. So you can basically provide a start point in time and an end point in time, and then these filters are going to retain all all the events that fall into that time range. There's one sort of thing though. There's we in the end we programmed three different functions or modes in which you can run this time range filter. So you can event it on you can run it on an event level. So that just retains all events that fall into the specified category. So that means that it can be the case that you're cutting traces. In the same way that if you did this attribute filter on the event attribute on the event level, then you could also potentially start cutting traces because you remove events that don't fit. The same here. So in a way, this can be seen as an attribute filter, but it's just more specifically, allowing you to specify a clear start and end time range. So that's one part. So there's another mode that basically retains any trace in its entire in its completion, so it doesn't touch the trace if it has any event falling into the into your specified interval. And finally, there's a version that allows you to retain all traces that are completely falling into this interval, which is also pretty neat, because in some cases you might want to, I don't know, only check those cases that were executed in a specific year or a specific month, and then you just specify the time range as being that month, for example, and then pm4py will automatically filter out all cases that are not completely contained. So you're sure that all the traces you have are actually started and finished within that time range that you provide. And okay, this functionality again is fairly straightforward. So when we go to the first example that I've shown you, so you have to import the datetime library, standard library of Python, to specify timestamps. And the signature is very easy. Actually, you specify, you say, I want to do pm4py.filter time range. Then you give the log, you give the start point, the end point, and you give the mode. I think by default it's the events, so it will just retain the events that fall into the time range. Right in here, I'm saying I want every event that is somewhere happening on 31st of 20. I think it's happening in the 30th of December 2010. So if I've just executed that line, and I can already see that my filtered event log just contains 3 traces. And let's take a look. If we drill down, we observe that, for example, this trace here has, for example, this first event, which happened on the 30th of December 2010, and the second and third also. So apparently, this trace really got cut because originally this trace, which has a concept name value of 3, of course, contained more events, but I've been cutting off all events that are not happening on the 30th of December. And the nice thing with date time is if you want to specify, the start of a month, you can just remove the date, and I think it automatically takes the first date. So it's quite neat. If I'm not mistaken, I could be wrong though. But then, so as I said, we have also the option to filter all traces that are completely contained. The mode is called traces_contained, what's in the name. So if I'm now going to execute the statement that you're seeing highlighted on line 39 and 40, if I execute that, just done that, then you see I get an empty list because none of these traces, of course, all happen on that exact same day. We already saw that in my previous example, that only 3 traces were remaining. And finally, if you take traces intersecting, this is this function that retains the, also, let's say, all the traces that somehow have an overlap. So again, now I should retain 3 traces if I execute this function, because I've seen already that there were 3 traces that had some events on that specific day that I'm using, this 30th of December of 2010. However, it's very important to note that this traces intersecting will not cut those traces, where the events basically projects everything away that does not fit the bill. And I think I already lost the final check. So let me just quickly run it again. Always happens when you do. So yeah, now it's empty and now it's finished. It's probably because it's the last line of my script. So let's do this differently. Let's see how many traces we retain, and let's see for each t in print the length of each trace. Let's do it like that. I like to record my videos live and do minor editing. It's more fun. Sometimes you make mistakes. Well, mistakes happen. And now the question is, yes, so here's the final print of my final filter. So you see that here, the live demo effect. The length of the filter event log is 3, which is as we expected, because there were already, as we saw in the traces, in the event time range filter, we saw that there were in the end 3 traces having some events happening on the 30th of December 2010. However, here we see that one of those traces has length 9 and the other 2 has length 5. So these traces are remaining in their entirety. All right, so that concludes this tutorial. So we've seen various filtering ways, filtering techniques, and I think along the way we also extend the filtering. And if you have ideas or feature requests, by all means, share them with us so that we can, integrate your ideas into pm4py, which is only make pm4py better. And as you've also seen, as I typically videotape these recordings quite live, and I don't like to edit my videos too much because I have so much things to do. We saw a little demo effect glitch, but that happens, and I think it's actually funny. So I'm not going to cut it. I'm actually wondering who's actually going to check this video all the way to the end. And if you do, then I don't know, send some thumbs up or say I've watched it to the end. If I had pm4py shirts, I would totally try to randomly distribute them among the people that say the thumbs up. And I've seen that you've been talking a bit longer, but I don't have pm4py t-shirts yet. Also, if you think it's cool to have a pm4py t-shirt, let me know, because I can probably get them printed somewhere, although COVID probably doesn't help shipping at this point in time. Anyway, thanks for watching this pm4py tutorial, and I hope to see you next time. And in the next video, I will be showing you how to export event data. It's pretty easy, pretty simple. And after that, we will be actually looking at process discovery. So that's when actually the real fun begins. So thanks for watching, and hope to see you next time.